Okay, section 3.5 talks about two basic theorems that we need to look at involving parallel lines. One involves three parallel lines, the other one involves two perpendicular lines. So we'll get to them right now. So the first theorem, and again, we're not going to name them anything, it's just the first theorem. Okay, so first theorem. The first theorem states if two lines are parallel to the same line, so this is the first theorem. If two lines are parallel to the same line, then all three are parallel to each other. Then all three lines are parallel. Okay, so how does this look? Well, if two lines are parallel to the same line, so let's say we have a line here, we'll call it L, and we have a line here, let's call it M. And we say, okay, well, there's this third line over here, let's call it N. And I'm telling you two things. L is parallel to N. And I'm also telling you that M is parallel to N. Well, look at N. N already has one little arrow on it, so M gets that one little arrow. And M is parallel to N. So then what can we conclude? Okay, let me make that M a little bit better. What can we conclude here? Well, if L is parallel to N and M is parallel to N, then we know that L is also parallel to M. And that's sort of the conclusion. Okay? So now we know that all three lines are parallel to each other. Okay, and that's the first theorem. Pretty basic. All right, let's go on with the second theorem now. Okay. Second theorem states in a plane, so we have to be coplanar. So that's why it says in a plane. So we're on the same plane. In a plane, if two lines are perpendicular, if two lines are perpendicular to the same line, then they are parallel to each other. And notice here we have perpendicular, but then we end up with parallel. Okay, so it's not like the same one. It's not all about parallels. It's if two lines are perpendicular to the same line, then they are parallel. So let's draw this picture down here and let's talk about it. So here's my first line. And again, let's call it L. Okay, and it is perpendicular to, say, this line. Let's call it T for convenience. So they are perpendicular. So I know that L is perpendicular to T. Remember, that's the perpendicular symbol, the upside down T. And let's draw another line perpendicular to T. Let's call it M. I'll do better drawing as I go along. M. So we know that M is perpendicular to T. So the question is, what can we say about L and M? Well, I would draw your attention to where I put the right angle boxes. We need to identify what kind of angles those are. Let's label them 1 and 2. What kind of angles are 1 and 2? Well, if L and M are your two lines and T is your transversal, 1 and 2 are corresponding angles. So angle 1 and angle 2 are corresponding angles. And they both have a measure of 90 degrees, which means if they have the same measure, then they are congruent. And if they are congruent, we can say that the lines L and M are parallel. And that would be by the converse to corresponding angles postulate. Right? But this is the conclusion that we want. L is parallel to M. Those two lines that are perpendicular to the same line are parallel to each other. Okay? And that's like a little simple word proof. Okay, you could do a 2-column proof if you wanted to, but just a little word proof. Okay, so I'm going to do one example, and that's the video. So give me a second to write the example down, and we will begin. Okay, so here's the example, and again, I would take a moment to write this down, pause it, and then start again. But in this problem, we want to show that S is parallel to T. Again, this section is all about thinking. It's thinking how to prove things parallel, just like the section 4 was. Okay, so we're on the same idea. Well, if we look at the picture, what do we know? Well, I know that angle 2 is congruent to angle 3 is congruent to angle 5. I know that, right? By the congruent markings. And I also know, sorry, I'm getting ahead. And I also know that's a 60-degree angle. Okay? So the question is, how can we show S is parallel to T? Well, remember, we have the 3 converses. So we're going to have to use a converse to do this. So we have to use the converse of the corresponding angles postulate, alternate interior angles theorem, alternate exterior angles theorem, or the same side interior angles theorem. So let's see what we can do. Well, 5 is vertical with that 60-degree angle. So because of vertical angles, the measure of angle 5 is also 60 degrees, right? Because vertical angles are congruent, so their measures are equal. So this is 60. But then look up here. All of those angles are congruent. So that means that this is 60 and this is 60. Okay? All right, so we're there. Now, there's many different ways to look at this. I'm going to look at angle 1 now. Okay? This is a straight line. Right? S is a straight line. So it has how many degrees? S has 180 degrees. So S has 180 degrees. So that means that 1, 2, and 3 have to add up to 180 degrees. Well, if I take the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, I should get 180 degrees, right? Because they form that straight line. So the measure of angle 1 plus, this is 60 degrees, this is 60 degrees, so together that's 120 degrees, should be 180. And if I subtract the 120 away from both sides, I should get that the measure of angle 1 equals 60 degrees. So this is a 60-degree angle as well. So now there's many different ways to say this, but let's just compare 1 and 5 now. Okay? Let's look at angle 1 and angle 5. What kind of angles are they? Well, they slide down the transversal. Angle 1 and angle 5 are corresponding angles. Angle 1 and angle 5. They have the same measure. They're both 60 degrees, so that means that angle 1 is congruent to angle 5. And if corresponding angles are congruent, then your lines are parallel. S is parallel to T, and this is by the converse to corresponding angles postulate. Okay, so we'll look more at these kind of problems in class, but for right now, that's all I need to know from section 5. All right, thanks for watching. We'll see you.